before we start next in 4 o'clock, I should announce that the dinner is being slightly postponed because we're running late. So if you're hungry, now you're even hungrier, but sorry about that, but you know, there's also math that we have to understand and important things. But so anyway, without any further ado, right, so the dinner has been postponed until 7:15, to summarize.
Okay, thank you. So this time I'm going to put together hopefully by the end of the talk, I will have put together the computations in the Fukaya category that I was talking about this morning, how they fit with the deformation theory that Nati told us about, and hopefully by the end, how this also fits with the B model and how we start seeing equivalence between A and B models. So I'm going to say what algebraic structure we have. So our grading group is going to look like this. Our ring looks like this. And the vector space on which we're going to be looking at A infinity algebras is this exterior algebra where the degree of theta I is like this. Again, one in position I. So note the degree 0 part of this ring is the formal power series ring generated by this variable. Because that one, if you add up all the degrees here, you're going to get 1, 1, 1, 1, 1 here, and that's going to get killed in this quotient. All right. So also recall, let me write this one up here.
Small matter, but I just don't understand. You factorize by 2 times 1 minus n embedded. How is embedded? It's embedded in the first component. Factorization.
Is here?
Yeah. Now the quotient by.
Yeah.
It is embedded in the first component.
Yes.
So why do you write norm y is 2 times 1 minus n? It's already 0 in the graded group.
Sure. So I could write this. So sorry, this is the sum of these two.
Okay.
So I could also write this as.
I thought it separately.
No. Yeah, I probably. Yeah.
No,
Okay. So. So another thing from Nati's talk was that with this exterior algebra, we have this Hochschild-Constant-Rosenberg map from the Hochschild cochain complex to polyvector fields on n-dimensional space. And this sends and this is how it looks on the cochain level.
Now, is the differential 0 on both sides?
The differential is 0 on this side.
Okay.
On this side, it's the Hochschild differential.
Okay. On the right side is 0.
Yeah. On the right side, it's 0.
Yeah.
And this map
There's a more.
is a quasi-isomorphism. And so I should say the degree, so we already know what the degree of the theta I are. When we trace through degrees, we find degree of Zi is like that. Okay, so now let me say the theorem. It's going to be crucial for us. Okay. If we have an R-linear A-infinity structure on this A tensor R, so let me call this G. It's graded with this group, which remember means mu s has degree 2 minus s in here. The second thing is it has to be equivariant with respect to the action of the symmetric group, just permuting these generators theta 1 through theta n. The third thing is maybe I should have said if we write mu0 for the part that has no powers of qi in it, mu1 that only has a linear term in the qi in it, and so on. Then mu20 should be the exterior product on A. Finally, if we take the HKR map and apply it to mu greater than or equal to 3, we should get product of Z1 through Zn plus the sum of Qi times Zi to the n. That's the linear term in the Qi. Plus higher order terms, whatever they may be. And the conclusion is that if we have two A infinity structures that satisfy all these conditions, then there exist first, a formal power series in T whose leading order term is 1, and second, an R-linear A infinity quasi-isomorphism where this psi that appears in the formula is some automorphism of the coefficient ring R that sends Qi to Qi times this formal power series phi.
T is before product of Qi.
Yes, T is the product of the Qi, which has degree 0, so this is a graded.
What's psi?
Psi
Metamorphism.
is an automorphism of R.
Somewhat of
Yeah, I'll prove the existence of this automorphism. Well, I'll prove the.
It's not something you defined before.
No, it's not. It's something we'll define. We'll prove order by order the existence of the coefficients of phi that make this statement true.
Just I'm asking like what it depends on psi. Or is it important?
It depends on mu and m. So we'll show that as long as mu and m satisfy all these conditions, you can find an A infinity quasi-isomorphism between them, but only if you
Twist.
put this
Yeah.
correction, this change of variables in the array. Okay. So maybe just to make sure we're all on the same page, the point is this endomorphism of algebra of our Lagrangian, we're going to show has all these properties. the endomorphism of a matrix factorization, exactly like in Lena's talk, is also going to have all of these properties. And therefore, we're going to get this isomorphism. And this is going to be what so now we are going to have some equivalence between parts of a part of the Fukaya category and a part of some category of matrix factorizations, which will correspond to some part of category of coherent sheaves. And then we're going to show that these parts generate the whole category. And on the Fukaya side, that's going to be a result of the talk Cedric just gave. And on the B model side, Uri is going to talk about that tomorrow, why the things generate on that side. Today, still? Oh, okay. Oh yeah, that's right. Okay. So let me explain why this is true. So the first thing to do is say if we've got mu and m like this, then just setting all the qi equal to 0, we get an A infinity quasi-isomorphism between these two guys. So like this. And here, this is a direct application of what the result Nati stated. So first, using all the gradings that I just wrote up on the board, you can just check that the S, the A infinity operation with S inputs can only be non-zero if S is congruent to 2 mod n minus 2.
You want to say non-zero. You just wrote they're equal.
Sorry. Yes.
Okay, no.
Yeah. Okay. So in particular, I think Nati denoted this by the S obstruction class. So we get this guy in HH2 of our algebra A.
Sorry, but you don't want to say S, you want to say N in the last one.
Thank you. So again, we know what Hochschild cohomology of this guy is by our Hochschild-Costunt-Rosenberg isomorphism. And we can, we can compute that it's generated by this product of the coordinates z1 through zn when s is equal to n, and is 0 else. So Nati explained in his talk well, sorry, maybe first I should say that by this condition on our A infinity structure, the nth obstruction class of our guy is precisely equal to the generator of this part of Hochschild cohomology. So okay, does that make sense? Yeah, I'll leave that on the board for the moment. So the next thing we need to do is study the higher order parts of the A infinity structure in QI.
Why don't you need some flow in this case?
Why don't I need?
Matthew's talk, there was this action, C-star action.
So the C star action was by rescaling the.
You see the constant.
Yeah, the constant is 1 because we declare it to be 1. It's plus or minus 1, but you can do an automorphism, change the sign of one of the variables. It's okay. So the fact that this is an A infinity structure, we expand it out in degrees of QI. Means the bracket of mu naught with mu 1 is equal to 0, which means that mu 1 gives a well-defined class in Hochschild cohomology of A with the A infinity structure mu naught. And this is called the first order deformation class. This? So we have this A infinity structure that we can expand in powers of the QI. And the A infinity equations say when we take the Gerstenhaber bracket of this guy with itself, we get 0. So expanding this Gerstenhaber bracket out, the 0th order term says mu naught bracket mu naught is 0, so mu naught is an A infinity structure. The first order term says mu naught bracket mu 1 is 0. And the Hochschild differential on this guy is bracket with mu naught. So this is saying Hochschild differential of mu 1 is 0. So it gives us a class in Hochschild cohomology. Okay. So if M denotes the maximal, this maximal ideal in R, then, oh, I really should have written, well, this guy has some, okay, well. All right, really I should have written that like this. This mu1 lives in the maximal ideal, tensor A, and it's closed in Hochschild cohomology. So it defines a class in Hochschild cohomology of A with mu naught, tensor the maximal ideal modulo its square. And the point I want to make is that this thing has degree 2 with respect to our grading in this big abelian group. And now, furthermore, it's also, maybe this is bad notation.
So why does it have degree 2? Just because M1 has degree?
Because this whole thing has degree 2
Okay.
in Hochschild cohomology. And furthermore, we put this assumption that this thing was sim n equivariant, so this lives in the sim n equivariant part of this guy. And in fact, this class mu1 generates this thing. As a module over C of t. So this whole thing, so remember C of t was the degree 0 part of our coefficient ring R. So in particular, taking, sorry, not C of t module, because we're quotienting by this. Just C vector space. Sorry, I'm getting ahead of myself. That's correct. In the appropriate, yeah. So if we just forget about mu naught, well, sorry, I should really say what I. So this is what I really want to know. So if we take Hochschild cohomology of A with the A infinity structure given by mu naught, tensor it with R, and take the part in degree 2, and that is sim n equivariant, it has this class in it that come the first order deformation class of our structure here. Also, you can always multiply anything in here by an element of this degree 0 part of our ring. It's degree 0, it's equivariant, so it's always going to act on this guy. And in fact, this mu1 generates that. And the proof is that, in fact, is that by definition, we have this, the image of the first order part of mu under this HKR map is given by this guy here. Sorry, not first, leading. Now, what do I mean to leading order in the length filtration? Well, we have this.
4 relates to part of mu of degree bigger than contribute.
Yes.
Now you're talking something about, I see, okay.
Degree n.
Degree n, okay.
Yeah. So we have this filtration on the Hochschild cochain complex that's already been mentioned in Amitai's talk, for example. So this gives us a spectral sequence whose E1 page is Hochschild cohomology of A as an associative algebra, and which converges to Hochschild cohomology of the A infinity algebra A with mu naught. And what this thing tells us is that this mu1, this first order term of our A infinity structure, when you look on the E1 page of the spectral sequence, which is just our given by Hochschild Costunt-Rosenberg, it's given by this guy here. So it's given by this guy plus higher order in the length filtration. It's this filtration.
So when you write the E1 page is the Hochschild cohomology of the algebra, you mean with mu1 naught and mu2 naught, that's it? Or
No. You consider mu star naught, but you consider it as an infinity algebra.
yeah.
So using this spectral sequence and using the fact that we know the Hochschild cohomology of this guy by Hochschild Costunt-Rosenberg theorem, we can prove this result just by
Let's say it's sufficient to check it in U1 term.
yes.
Because if it's true in one term, it's automatically true.
Yes, exactly. So the degree 2 sim n equivariant part of this guy is equal to is spanned by these two classes. Okay, and now this class was our obstruction class for mu naught, and so you will see that as you go, when you go to the nth page of the spectral sequence, this class will get killed by the differential in the Hochschild differential. So this guy gets killed on En. This guy remains, and this is the class that is our first order deformation class. So on the En page, this mu1 generates, and therefore it generates in the whole complex.
When you can say degree 2, what is degree here? Is degree in kind of Hochschild complex, or degree in terms of a group G?
The group G.
Okay.
Which maps to Z by just projection on the
Yeah,
left component?
No, because it's Z.
it's quotient by sampling diagonal.
Ah,
Yeah.
Quotient by sampling diagonal.
So you can map it to Z by making some non-canonical choice, but you kind of need to keep track of all of them together to get this result.
so whenever you write grading here, you really mean.
In G.
G is what that is.
So what is 2 in G?
2 is in G, it's a period component.
Okay, so it's 2, 0.
Yeah.
Okay.
Exactly, yeah. So it's in here, it's 2, 0.
Yeah.
And in particular, you know, this kills a whole lot of your complex because, you know, any degree in here that doesn't get killed in this quotient is going to mess you up. Yeah. Okay. So now we need a generalization, a similar result to what Nati proved in his talk. So if we've got two minimal A infinity structures, that means the differential vanishes, as it does for grading reasons in this case, which coincide toward a 0, which we showed we could arrange. Possibly with some group equivariance here.
Generates over C of T.
Maybe I should just state the theorem for the particular arrangement that we have. maybe I can do something slightly simpler for just to make the notation simpler and just assume that I'm only deforming this guy over in one direction. So this is a perfectly useful theorem. It's just to actually apply it, I need all these crazy gradings in the picture. Sorry, not mu naught. Then we can construct this psi and this A infinity functor between these two guys, A infinity morphism. And the proof is by constructing this guy F order by order in T. So we start with F naught equal to the identity. Then inductively suppose sorry, I should start back over here. So inductively suppose So suppose that this equation holds up to order D. Then you want to try to make it true to order D plus 1. What you're going to find is that so you have this, so you've chosen F naught, F1 up to Fd, and you're trying to see if this equation is true to order D plus 1. So you collect all the terms of order less than or equal to D. So if this were equal to 0, you would be done. But in general, it won't be. Instead, what we need is to add some F D plus 1 that's going to make it equal to 0. So this term, So m naught equals mu naught. So this whole term here is the Hochschild boundary of fd plus 1. So that means we can kill this term if it is equal to a Hochschild boundary, if it vanishes in Hochschild cohomology. So you can prove that this term is closed in Hochschild cohomology, but not that it necessarily is a trivial cohomology class. Instead, yes, the mu naught Hochschild cohomology. Instead, this is going to be t to the d plus 1 times some class which is closed in Hochschild cohomology but not exact. But what you can now do so this is so by hypothesis, this guy is generated by the first order deformation class of our guy. That was our hypothesis. So now what we're going to do is make a substitution that looks like this. The effect of that is going to be replacing mu1 times t by mu1 times t plus mu1 times this, whatever constant we choose, times t to the d plus 1. So by making this substitution in the coefficient ring, we can make this guy exact in Hochschild cohomology. And then we can choose our fd plus 1 to kill it. Okay. So this completes the proof of the theorem. By doing a version of this argument, but taking into account this funny coefficient ring and this sim n equivariance, but the same thing works. So the final result I want to say is that when we take this immersed Lagrangian sphere L, this has the properties enumerated in the theorem. In particular, when we prove that the corresponding endomorphism algebra on the B model also has the corresponding properties in the theorem, it'll prove that they're the same up to this mirror map automatically. So the proof is so since it's a relative Fukaya category, it's G graded. This was something I explained in the first talk. Since this you have the symmetric group acting on this Lagrangian just by permuting the coordinates of the CPN minus 1 in which this guy sits. There's an obvious SymN action. It's actually a little bit subtle to make it strictly equivariant rather than equivariant up to homotopy, but you can get around that. I proved this morning that the product at order 0 is the exterior product, so we're fine with that.
The product order 0, you don't know anything about divisor, you just remove.
That's correct. Yeah, you're removing the divisor completely. The other thing we proved this morning was this. This is also in the complement of the divisor. So we have the first bit of this guy here. But now the final thing we proved was that
not dn,
exactly.
Yes.
So this means that when we apply the HKR map to mu1, order 1 component, we get sum of qi times zi here. And that...
But this one works. We have two different infinity algebras. One with d, other with dn.
That's right.
How do we go? When you write here, is it in d or dn?
This is in d.
D. Okay, fine.
Yeah. So indeed, we're working in with a different condition along the divisor here, and indeed we get a completely different answer. So now we need to understand what happens when we turn on orbifolding around the divisors, rather than just counting curves going straight through them. suppose we've got this class in Hochschild cohomology. That's the first order deformation class of our relative Fukaya category. That's given by counting disks that just hit divisor di and no other divisors, and only hit it once. So maybe let me call this alpha I. Let beta I be the first order deformation class.
Isn't it the same? Right, the same new one I.
So maybe I should put an extra decoration here then.
Really fx minus d means with different coefficient rings in both. Right. Here it's only the 0 order?
It's the 0th order, yes. In both cases, yes. Yeah. Same thing, except where we have an orbifold Fukaya category down here. So this one counts disks that hit di, but hit it with order ai, with n in our case. Then beta I is equal to alpha I to the power ai, where power means multiplication with respect to the Uneeda product in Hochschild cohomology. Okay. In particular, this proposition finishes the proof of this guy. Because here we show that for CPn-2D, the deformation class is Zi, and the Uneeda product on Hochschild cohomology goes to the thing that you expect under the HKR isomorphism. So the deformation class for this orbifold guy gets taken to the nth power, which is Zi to the n. So let me finish by explaining the proof of this proposition. First, a formula for the Uneeda product. Sorry, I shouldn't use psi either. Let's see. This is probably a bad idea too, but anyway. Well, I shouldn't say that. So here is a formula for the Uneeda product. So if I take Hochschild cochains F and G, so they take in a bunch of inputs and spit out an output, the Uneeda product of them when we take in a bunch of inputs, the output is given by taking the A infinity structure, mu, and inserting all these guys with an F inside here on the left and a G inside here on the right. Summing over all possible ways of doing that gives you this product.
There are kind of dots between F and G.
Yes.
It means you put some number of F and some number of G.
No, one F, one G, but there are some inputs here. Yep. Okay. Now we're going to consider a moduli space where the output point is going to lie at -I, and we're going to have two internal points lying on the real axis at t and -t. And at this one, our disk is going to hit di, and at this one, it's going to hit di with multiplicity a-1. So this defines an element of Hochschild cochains on the Fukaya category of the complement. So the coefficient of the cochain that takes in these inputs and spits out this output is the number of these holomorphic disks. Furthermore, if we take, instead of the zero-dimensional component of this moduli space, which we count to get this element here, we look at the one-dimensional component. It has boundary given by boundary components where t goes to 1. These 2 points stretch all the way apart and bubble off each a disk of their own. It also has a boundary where t goes to 0. So in principle, a holomorphic sphere could bubble off when these two marked points come together. But in fact, this would be a holomorphic sphere that would only be allowed to hit divisor di. But there are a whole bunch of other hyperplanes in our manifold that it's not allowed to hit, so it has to be a constant holomorphic sphere. And its intersection multiplicity with di has to be the sum of the multiplicities here, which is a plus 1. And finally, you have boundary points where t is between 0 and 1, which is where a holomorphic disk bubbled off sometime in between those two. And now here, this is alpha I. Maybe I should. This is maybe I should say B I comma A for this guy. And this one is our A infinity product. And these guys here exactly correspond to the terms in this Uneeda product. So this is equal to alpha I times beta IA. This one is equal to beta I A plus 1. And this one is equal to the bracket of the A infinity multiplication with mu 0, yes. So since the sum of the boundary points of a, it's this guy given by counting the zero-dimensional component. So in particular, alpha I cup beta IA is homotopic to beta I A plus 1. Which means, by induction, that beta IA is the Ath power of alpha I. So this completes the proof of that proposition, and therefore that our Lagrangian fits in that sort of recognition principle I stated at the start. Okay, I'll stop there.